We will look at several examples of formulating dual problems, and using those examples we'll demonstrate several properties. The first property that I want to demonstrate is that the dual is formulation dependent. In other words, it depends on how you formulate the dual problem. For instance, consider the problem min over x minus of I equal to 1 to m log of bi minus ai transpose x, where ai and x are two vectors. Now in this problem, this is an unconstrained problem. There are domain restrictions, of course, but that's it. We don't have any other constraints. So there is not much point in formulating the dual because there are no dual variables here. However, we can formulate a dual if we slightly modify the same problem. So for instance, we could write the equivalent problem as minimize x comma y minus of summation of I equal to 1 to m log of yi, where y is equal to b minus ax. So I have collected all the b1 to bm into the vector b, and likewise the rows of a are a1 transpose to am transpose, and likewise x. So this is the equivalent problem. So these two are equivalent, and now we can actually formulate the dual. So let us do that. Let us formulate the dual. Let's associate the dual variable nu. Nu would be a vector in Rm with this. So we are considering this problem. If we associate the dual vector, then the Lagrangian is given by, note that the x and y are primal variables and nu is the dual variable. So the Lagrangian is given by minus log of yi plus summation of nu I equal to 1 to m times yi minus bi plus ai transpose x. Note that this equality can be written in the opposite way also. We can also write it as b minus ax equal to y, and that would lead to some other dual problem, which would again depend on how you write the inequality, but it would lead to an equivalent dual problem. So this can be grouped like this. So what we can do is we can write I equal to 1 to m nu I yi minus log of yi plus summation of I equal to 1 to m nu I times ai transpose x minus nu transpose b. So I've just collected nu I bi summation as nu transpose b. So now there are three terms. So the purpose of putting these terms differently is to group them according to their dependence on the primal variables. In particular, observe that this part depends on y, this part depends on x, and this part is a constant with respect to x and y. It depends on nu, but it is a constant with respect to the primal variables. This is often the case in the case of Lagrangian. So Lagrangian is often separable in terms of the primal variables, and that's what makes minimizing the Lagrangian easy. For instance, in this case, if we minimize with respect to x and y, you can observe that we can separately minimize with respect to y and separately minimize with respect to x while ignoring the constant term during the minimization. So that is only possible because x and y appear in separate terms. In other words, if we calculate the dual function, it would be given by minimize with respect to x and y of lxy nu, which can be written as minimize with respect to y of I equal to 1 to m nu I yi minus log of yi plus minimize with respect to x summation of nu I ai transpose x minus nu transpose b. So we have separated out in terms of x and y, and in fact the first term can be further separated because each of its summands depend on a different yi, right? So further separation is possible, and we can interchange the minimization and summation. So we can interchange the minimization and summation operation. So the reason we can do that is because each of the terms depend on a different optimization variable. So we have summation of minimize over yi nu I yi minus log of yi, right? And that is not the case here. Here all of the terms depend on x, but we can write it in a different way. So what I want to do is write it as minimize over x, but in this summation, which is from I to equal to 1 to m, I want to collect all the terms that depend on I. So I want to write it as summation of ai nu I. ai is a vector, so summation of ai nu I would be a vector transpose x and minus nu transpose b, right? So please verify that this is indeed the case. This is just another way of writing the same thing, and in the first case we have interchanged summation and minimization. Now let us solve each of these problems separately. So what is the minimization of yi? Nu I yi minus log yi. What is the solution of this problem? To see this, what we can do is simply differentiate it with respect to yi and set it equal to 0. We must, however, remember that yi is greater than equal to 0. That is the implicit constraint. So if we differentiate it with respect to yi, we will get nu I minus 1 by yi equal to 0. Or in other words, yi equal to 1 by nu I. But yi equal to 1 by nu I is not always valid. In fact, it is only valid because of the implicit constraint. It is only valid when nu I is greater than 0. So when nu I is greater than 0, then the minimum of this objective is indeed attained at yi equal to 1 by nu I. However, if nu I is negative, then this is not the case. So in case yi is equal to, so in case nu I is greater than 0, let us also substitute it back, and we will see that this minimization is equal to nu I times 1 by nu I minus log nu I, 1 by nu I. So which is basically 1 plus log nu I. So in case nu I is positive, then it is 1 plus log nu I. If nu I is negative, then, so in that case, you can observe that the function looks something like this. So let me plot this function here. On the x-axis I have yi, and on the y-axis I have the objective function, which is nu I yi minus log yi, and you can see that it would look something like this. In other words, it decreases to minus infinity in that case as yi tends to infinity. So in this case, it is unbounded below. So if nu I is less than 0, it is unbounded below. So in other words, the minimum value of yi greater than equal to 0, nu I yi minus log yi is equal to 1 plus log of nu I whenever nu I is greater than 0, and minus infinity whenever nu I is less than equal to 0. So that is the solution of the first subproblem. So there is a scenario where the first subproblem turns out to be minus infinity or unbounded below. Then let us come to the second part. So second part is minimization of, so remember this is the second part. So minimization with respect to x of summation I equal to 1 to m ai nu I transpose x. Now, for the sake of just simplicity, you can imagine this to be C. So what is the solution of minimize with respect to x, C transpose x? We have already seen this kind of simple problem many times. This is basically always minus infinity, right? This is always minus infinity unless C is equal to 0, right? So in that case it is 0. So this is 0 when C is equal to 0, and it is minus infinity when C is not equal to 0. Or in other words, ai nu I summation over I is not equal to 0. This is minus infinity, and whenever ai nu I summation over I is equal to 0, then it is 0. So again, there is a scenario where this is minus infinity. Note that another way of writing down this condition is that A transpose nu is equal to 0. So that's another compact way of writing down this condition. Now let us add together all the terms that we had. So let us write down G nu as, in the first case we had the summation of 1 plus log nu I. So we have summation I equal to 1 to m 1 plus log of nu I. So that was the first term. The second term was 0, and the third term was minus B transpose nu. So we have G nu equal to this if nu satisfies certain properties. First of all, we require nu I to be greater than equal to 0 for all nu, and second, we require A transpose nu to be equal to 0. So under these two conditions, this is the dual problem or dual function, and it would be minus infinity otherwise. So if any of these two conditions are not satisfied, G nu would be minus infinity. So this is the dual function. Now what does it mean for a concave function to be minus infinity? To appreciate that, recall the extended real valued definition of a function. So if we had a convex function, we said that f tilde is the extended definition, where we said that this is equal to fx for x in the domain of f and infinity otherwise. If we are talking about a concave function, then we can similarly define g tilde of x as gx, such that x is in domain of f, domain of g, and minus infinity otherwise. The reason we have to define it to be minus infinity is because minus g of x is a convex function, and therefore minus g of x should take value infinity if x is outside the domain of g. So therefore we have defined it as minus infinity. So this definition, what we are seeing here, looks very similar. So in fact, looking at these two and comparing, we can see that the domain of G is equal to the set of all nu, such that G nu is not minus infinity, it is not equal to minus infinity, but it is greater than minus infinity. And this is precisely the set of all nu such that nu is greater than equal to 0 and A transpose nu is equal to 0, which are the conditions for this to take a finite value. So now let us put together the dual problem. So the dual problem is given by maximize G nu, which is m plus summation I equal to 1 to m log of nu I minus B transpose nu, subject to constraints. The explicit constraints are not there because there is no inequality constraint, but there are implicit constraints saying that nu should belong to the domain of the objective function, right? And these constraints are written as nu greater than equal to 0 and A transpose nu equal to 0, because this is exactly the domain of G, right? So this is our problem, our dual problem. We have explicitly written down the implicit constraints in order to not specifically define the domain of G. So this is a dual problem with respect to nu. So we have observed two things from this example. First is that dual is formulation dependent. And you need to pay attention to, the domain of functions while calculating dual. Problem. So if you are evaluating or writing down the dual problem, it is necessary to pay attention to the domain or the points where the function takes minus infinity value.